Good morning, students. Welcome to another session of EE403 Distributed Generation and Smart Grids. Today we will see the various control functions for microsources and central controllers. Just introduction only. Before we proceed, let us see a quote by Dr. APJ Abdul Kalam. Winners are not those who never fail, but those who never quit. So today we will see module 2, second part, introduction to central controller and microsource controllers, and also we might enter into control functions for microsource controllers. This is the general scheme of a microgrid. So there is a common AC bus. So this is the common AC bus, and all the microsources are connected, and the loads are connected through feeders to this common bus. There will be some loads at the PCC also. So from the PCC, the main grid is connected through a static transfer switch. The central controller has communication with all the microsources. It is shown in dotted red lines, and can give necessary instructions to microsources. It can also open or close the static transfer switch, disconnecting or connecting the main grid. Each distributed generator has a controller, and we call it microsource controller, MC. Here you can see an MC, and here also you can see a MC. So this is the general schematic of a microgrid. Now the built-in control features of the microsource controllers are active and reactive power control, or we call it PQ control, voltage control, storage requirement for fast load tracking, and load sharing through PF control. So these things today we will discuss today. So the first one is the PQ control, or active and reactive power control. Now we need to control a microsource so that its real and reactive power output is constant. So this type of control is called PQ control. P stands for the real power and Q stands for the reactive power. All microsources behave like a voltage controlled current source. So the basic scheme for a typical microsource control is shown here. The voltage source inverter in the converter system controls both magnitude V and the phase angle delta 1 of the output voltage V angle delta 1 arriving at bus 1, or we say it is the converter terminal. The microsource supplies controlled power to the microgrid bus, we call it bus 2, at a voltage of E angle delta 2 through an inductor of reactance X. Now V angle delta 1 leads E angle delta 2 by the power angle given by delta is equal to delta 1 minus delta 2. The active power flow P is controlled by controlling delta, or basically the frequency. Okay, you should remember that the active power flow is controlled by controlling the frequency. The reactive power flow, which is Q, is controlled by controlling the voltage. The controls are based on feedback loops of output power P and E. The equations for P and Q are given here. This is the basic PQ control scheme of microsources. You can see that the output current and the grid voltage both are measured, and this block breaks it down to its direct and quadrature components, VD and VQ, and ID and IQ. So we calculate the direct and quadrature components of the output voltage and current using this block, and these quadrature components are used to calculate the direct and quadrature current set points, and P star and Q star denotes the active and reactive power requirement. So the feedback ID and IQ, they are compared with the ID and IQ set points, and the difference, which is the error, is used in the PI controller to produce the necessary VD star and VQ star, which are the direct and quadrature components of the voltages, and this is used to control the VSI. So this is a closed loop control system, and this is basically the PQ control of microsources. This is another scheme shown here. I am not going to discuss this scheme here. You should go to the lab and simulate this circuit and see how it works. Now the output frequency and voltage of the inverters follow the Droop characteristics as shown in figure. So this is the Droop characteristics, and what you observe here is whenever there is a change in frequency delta F, a corresponding delta P, which means the change in active power. So whenever there is a change in frequency from its nominal value of 50 Hertz, the microsource will change their output by delta P. Similarly, whenever there is a change in voltage delta V from the nominal voltage, the microsources will change their output by delta Q. So basically you should understand, a change in frequency is followed by microsource changing the active power by delta P, and a change in voltage delta V is followed by the microsources changing its reactive power by delta Q. This is a typical example of Droop control with two microsources and one storage device So this is microsource 1 and microsource 2 and a storage device. So you can see that F0 is the nominal frequency, which is 50 Hertz. So as the frequency changes, so the microsource or the microgrid goes to a new frequency, F new. In that case, so there is each micro source should supply a corresponding active power to bring back the frequency. So delta P0 has to be supplied by the storage device, delta P1 should be supplied by microsource 1, and delta P2 should be supplied by microsource 2. So the total active power to be supplied by various microsources and storage devices is equal to delta P0 plus delta P1 plus delta P2. And similarly in voltage control, so this is frequency control. In voltage control, Q of the grid is equal to delta Q0 plus delta Q1 plus delta Q2. Now the voltage control of microgrid is essential for the overall stability and reliability of microgrids. So if there are large number of microsources, a variation in voltage at different places will lead to reactive power oscillations, which will lead to circulating currents, and these circulating currents, if not controlled or regulated, will lead to the damage of microsources itself. So in a conventional grid, the circulating current is restricted by the large impedance between generators. But here in a microgrid, the impedance between generators is low, so the circulating current has harming effects on the microsources. In a microgrid, the feeders are mostly radial and the impedance between two microsources is small. So what will happen is this circulating current might exceed the rated current of the microsources, damaging the microsources or tripping down the microsources. Now these circulating currents can be controlled by using the voltage reactive power Droop controllers with Droop characteristics. So whenever there is a circulating current, the controller increases the local voltage set point when the microsource reactive currents become predominantly inductive and vice versa. So when the current is inductive, basically what we do is the voltage set point is increased. Now the question is how to set the Q max, the reactive power limits. Actually it is set by the VA ratings. VA rating is VAR or S of the inverter and active power output of the microsource as per this formula. So the Q max is equal to under root of S square minus P square. Now storage requirement for fast load tracking, this is also very important. In grid connected microgrids, the initial power balance during connection of new load is the responsibility of the utility generators. But in the islanding mode, the microgrid should ensure power balance through its storage devices. So the storage devices should act fast enough to ensure power balance. So DC storage devices are connected to the DC bus and AC storage devices are connected to the microgrid bus. So it is the duty of the microsource controller to use the storage devices for fast load tracking. So there should not be any power balancing issues. The fourth one is the load sharing through PF control. Now the microgrid controllers should ensure smooth transition from grid connected mode to standalone mode and vice versa. During this transition to standalone mode, the microsource controllers of each microsource exerts local PF control to change the operating point so as to achieve local power balance at the new loading. So each microcontroller will not wait for any command from the central controller. It will observe the frequency change and accordingly adjust the active power to achieve the load power balance, and it is done automatically. So load sharing through PF control, here active power versus frequency droop characteristics is shown here. PO1 and PO2 were the active power supplied initially. So when the frequency changes from omega 0 to omega 1, the new active power to be supplied by micro sources are P12 and P11. Load sharing through PF control. In grid connected mode, microgrid loads are supplied both from the main utility grid and the microsources. When utility supply is interrupted, so the microgrid will move into the islanding mode. And during this changeover, the voltage phase angles of the microsources also change, leading drop in their power output. So what will happen? The frequency also changes. So when the frequency changes, each microsource will quickly pick up its share of load without any power dispatch schedule from the central controller. Now, the Droop regulation decreases the microgrid frequency. So the microgrid controller should incorporate a control function to restore the operation to the rated frequency with proper load sharing. So these are some of the references you should go through. These are some of the abbreviations used in this presentation. And with this, we wind up this session. This is Dr. Unnikrishnan PC signing off. Thank you very much.